Hello everybody, welcome back to Creepy Screen. Today I'm going to finish Lecture 1 that we did not have time for in class due to an unexpected power outage. This material is not being covered in Homework 1, but it's something that I wanted you to have, so I thought I'd go ahead and finish the notes that I had given you. So just as a point of reference for where this begins, slide 62 in Lecture 1 here. This is talking about what the remainder of the lecture had just covered, which is describing the standard error for a sample mean as the magical quantity that allows us to go from the single sample's worth of data that we have into a broader population. The idea of a standard error is that it approximates the sampling distribution's amount of variation across samples of the same kind. So if I take a single sample out of a population and I take that sample's mean, it's not going to exactly match what the population mean is. It's going to be a little bit off. And if I do that repeatedly, I can form a distribution of sample means. The standard error is supposed to approximate the standard deviation of that sample mean distribution. It's how far off on average any one sample's mean is from the population mean. So standard error is an index of inconsistency or wiggle across samples, as I'm fond of saying. And what contributes to the standard error is the standard deviation of the variable in question. So if people are more spread out around the mean, if the standard deviation is higher, the standard error will be higher as well. And if there's fewer people, the standard error will be higher. And we used properties of the central limit theorem to describe how we can take this standard error and compute confidence intervals around the sample mean, and also to do hypothesis tests that compare the sample mean to an expected population mean. So the safest strategy that we learned is to use the t-distribution as the standardized version of the sampling distribution for the mean. T differs from Z in that it pays attention to how many people are contributing to the sample. So there are stricter criteria for smaller samples, and if you get enough people, T converges in distribution to be the same thing as Z. So in this case, if you have a big enough sample, or you know what the standard deviation of the population is supposed to be, you can use a z-test to do this hypothesis test to compare the sample mean to the population mean. Otherwise, which is almost always the case, most of the time, we would use a t instead. So everything that I've talked about with respect to this process is describing the means of quantitative variables. And I wanted to give you some additional cases related to this where we would use the standard error of a statistic to make claims about the sample relative to some expected population. So after this slide, we looked at examples using twinning effects of how this process would play out in research. Then I showed you the SAS and the Stata code, and here's where we're picking up with new material. This is slide 67 of lecture 1. So what about binary variables? Well, this is one instance in which we can take measures of central tendency that would be meaningful for categorical variables, and that's if the variable is binary, if it only has two choices. And almost always in binary variables, people are talking about those two choices being a 0 or a 1. And in those cases, the mean of the binary variable y bar gets relabeled as p, which is the proportion of 1 values, and sometimes the letter q is given to the proportion of 0 values. So just like in regular quantitative variables, you would expect that the sample size relates to the standard error, but in binary variables, the proportion of ones, or the sample mean, also relates to the standard error because a binary variable has only two possible values, and the variance of the binary variable is a function of the mean. So the calculation for variance in a binary variable is p times q, the proportion of ones times the proportion of zeros. So to show you what ends up happening with respect to the standard errors of the mean for binary variables, I have another set of fake data. So I created two fake variables, for a sample of 100,000 fake people. And the one on the left has a mean of 0.6 and the one on the right has a mean of 0.2. So that means all I need to know with respect to the variability of these two variables is contained in the mean. For the variable on the left where the mean is 0.6, its variance is 0.24, and for the variable on the right where the mean is 0.2, its variance is 0.16. And by the way, the type of distribution that goes along with this idea of a binary variable is called Bernoulli, and it's capitalized because that is, yet again, another person's name. So I took random samples from this population of different sizes, and I did for each size 1,000 resamples to create the pictures that are shown here. So what you're looking at are the sampling distributions for the mean of this binary variable in samples of 5 people, 10 people, 15, 20, 30, or 50. And you can see that as sample size increases, this distribution becomes more symmetric, more normal looking, and the values get closer together. But it doesn't work so well when you have really small samples. And the variability of the sample mean, so how discrepant one sample's mean is from each other, is highest when you have the fewest people. So on the right-hand column here is the standard deviation of these means, how variable the means are from each other. So on average, how far off any sample mean is from the population mean. So this is the standard deviation that the standard error is to approximate, and it's highest when you have the fewest amount of people. But this is for a binary variable that is relatively equitably dispersed, where the mean is 0.6. What happens for the other one where the mean is only 0.2? Well, it looks a little weirder. Now we get into problems of skewness because a mean of 0.2 means that most of the cases are going to be on the low end. And so these distributions look a lot less normal, particularly with smaller samples. And it turns out that these distributions are actually known as something else. They are called binomial distributions, where the binomial distribution has two parameters. One is the mean, and the other is the sample size. And so you end up with skewed distributions in this case. The same premise holds, though, in terms of the fewer people, the larger the standard deviation across samples of each of these sample means. So in these pictures, you can anticipate that trying to use a normal approximation for these sampling distributions probably isn't going to work so well, particularly for smaller cases. So what do we do instead is a $10,000 question. So when you have enough cases, and you can't see my air quotes, but that's what I'm making. So in this picture, you get 50. It looks reasonably symmetric and normal-ish. In the previous picture, it started to kind of come together around 20 or so. There are rules that have been developed as to when, for binary variables, you have enough data to be able to use a standard normal approximation. And that's when the sample size times the proportion of ones, n times p is greater than 5, and sample size times the proportion of zeros is also greater than 5. I also found greater than 10 as a reference in some sources, so clearly there's some disagreement. In those cases, you can use a z standard normal distribution to form confidence intervals and conduct hypothesis tests regarding the mean of a binary variable. And this is what I'm demonstrating in the subsequent slides. I ended up not doing this for homework 1, so you can disregard that part. Otherwise, what to do instead is a bunch of different things. There's a whole bunch of different approaches that have been proposed for what to do instead when you have small samples and a standard normal approximation for the sampling distribution isn't going to work as well because it looks binomial instead. Interestingly, none of these involve the t-distribution. I'm honestly not sure why that is, so if anyone's listening out there in YouTube land who has the answer, please send it to me. These involve things like continuity corrections and exact statistics. These use resampling techniques to be able to empirically derive what the standard error would be rather than using a normal approximation to give it to you. I've given you some links to some additional documentation on these issues, and if you're interested more generally, I would look up under the search term for the Google categorical data. I've given a few of you a reference to the Agresti Classic Categorical Data book That would be a good source to look at some of these issues, and I'm sure there's even more recent work that's been done on this problem as well. So here's what it would look like if we used the standard normal approximation to test the mean of a binary variable relative to a population mean. Just like we used in SAS proc_freq to get frequency tables and percentages, we're going to use proc_freq in this instance as well, but there's an extra piece that's being added to the command. So this information on the table statement after the slash is new. So just to walk you through what this command is doing in SAS, proc_freq is the command. In SAS, you always need to tell it what data set you're referring to. The table statement is like the var statement in other procedures where you list the name of the column that you want information about. And this example is asking whether or not the proportion of high school non-graduates in the general social survey data that we're playing with is different than 0.10. So I'm just arbitrarily saying that I have some expectation that the percentage of people who did not graduate high school should be 10%. So I'm going to compare my sample mean against that benchmark as my null hypothesis. So to do so, we use the binomial option on the table statement here, and I'm telling it which category of the variable I want to test the mean with respect to. So I want the proportion of people who have a value of 1 in this variable, and I want to compare it against a population mean of 0.10, and I want to do so using an alpha level for where unexpected begins of 0.05, and CL means please also give me a confidence interval, or a confidence limit as it is called within SAS. So the first table here summarizes the frequencies of this binary variable. The binary variable is coded such that if you have more than a high school degree, that's a 0, and if you have less than a high school degree, that's a 1. So 12% of our sample has less than a high school degree, and we want to compare that 12.4% to the 10%. So phrasing that percentage as a proportion, the information given for the test is in this box right here. So the proportion for the sample is 0.12. The standard error for that proportion is 0.01. So note that I'm saying it's the proportion, but it means the same thing as the sample mean. It just gets a different phrasing for binary variables. So this is the sample mean, the proportion of 1 values, and I have a confidence interval around that. SAS also gives you the exact confidence interval. This will not match Stata's output exactly, and so I'm not going to ever ask for that, but just as an FYI that this is trying to do corrections to account for potential problems in the results due to small samples. The hypothesis test information is in this third box over here, and it gives me a z value that corresponds to a standardized version of how far off my sample's mean is from the population mean in standard error units. And note that the standard error that it's using over here is the one that goes with the population standard deviation rather than the sample standard deviation, so it's a bit inconsistent. But here's the results if I were to phrase them. So the mean of the variable, the proportion, 0.124, there's the standard error that's using this mean as a way to get the standard deviation with which to compute this standard error. That results in a 95% confidence interval using a z of 1.96, given this alpha of two-tailed alpha of 0.05. My z value was calculated as follows. It's the sample mean minus the population mean that's expected as the null hypothesis, divided by the standard error that it's using. That works out to be this 2.165. So 2.5 standard errors above the mean that's expected is what I found for my sample. The p-value for the two-sided hypothesis test that goes with this z-value is 0.0304. So what that means is that fewer than about 3% of the time, we'll say, we would find a sample mean that is as discrepant or more discrepant than the population mean. In other words, p-vet is less than 0.05, so this has crossed into what we have defined ahead of time as unexpected territory. So we reject the null hypothesis. We would say that not only our observed proportion of 0.124 is greater than the expected proportion of 1.10, but it's significantly greater because p is less than 0.05. The equivalence test in Stata requires less code, but it's a different command. It's PR test as opposed to t-test is what it was for quantitative variables. You need the name of the variable, two equals sign, and then the population mean that you're testing as the null hypothesis. Commas in Stata denote options in the same way that slashes denote options in SAS. And so level 95 is the Stata way of saying alpha of 0.05. So confidence level is 95% is what we're defining expected as. 5% alpha level is what we're defining unexpected as. So it gives you the mean, the standard error of the mean, given this mean. So this is the sample standard error, not the population confidence interval. The z-value from that information is right here, and then the two-tailed hypothesis test is given in the middle. So p not equal to 0.1, acknowledging that it could be too low or too high. And so then here's the same information given again. We would conclude that our sample proportion of 0.12 is significantly higher than the expected proportion of 0.10. If we wanted to phrase our hypothesis from the opposite direction, so rather than testing whether the proportion of non-graduates is different than 0.10, we could also test whether the proportion of graduates is different than 0.90. So just to demonstrate how to do that, I have so it's the opposite direction, but it's the same information. I'm using an alternative variable named grad high school, and in the videos, I believe it's part 2 of the videos that go with example 1, I explained how to compute these new variables. This is the opposite of the previous variable, so now 0 means that you have less than a high school education, and 1 means that you have graduated high school. So again, 12.4% of the people did not graduate high school. That means 87.6 did. And so in this case, we're comparing the 0.876 proportion to the null hypothesis of 0.9. And lo and behold, we get exactly the same z-value, but with a negative sign. That is as to be expected because this is the same test, just from a different perspective. So our previous test, we found that the proportion 0.124 was significantly greater than 0.10. This test is telling us that our proportion 0.876 is significantly lower than 0.90. So this is to say you can phrase it from either direction that you wish. One direction may be more convenient or more typical in your discipline. So the same information phrased from the opposite perspective, this proportion of ones that represents the number of people who have graduated high school, 0.876, is not only smaller than 0.9, but it is significantly smaller because we would find a sample mean as discrepant from the expected population mean of 0.90 less than 5% of the time. It would be 3% of the time to be exact. Okay. The same thing in Stata, again changing the variable, setting the new null hypothesis to be 0.9, same level of confidence, and we get the same z-value as from SAS with the same probability and the same conclusion. So in practice, there are two general ways that one would obtain a standard error for a sample statistic. So remember, a statistic is just a characteristic of a sample. We know about sample means, we know about sample standard deviations, we know about sample skewness. Those are all statistics. And in theory, each of those could get a standard error that describes its behavior across repeated samples of the same kind. So more generally, one way that we can find such standard errors is to rely on asymptotic sampling distributions. That's what we've been doing. When I say that people smarter than me came up with the formula and it works, and so we use it and believe in it, that's what I'm talking about. This term asymptotic means what would happen if we had an infinite sample, meaning the results get more and more prototypical to expected the larger the sample. Everything that we're going to do in this class and in actually most of my classes is going to use this sort of asymptotic approach, meaning that there are accepted ways to find the standard errors, either given these sorts of formulas or iterative algorithms that provide standard errors as a byproduct of the analysis. I'm talking about likelihood functions for those of you who might be familiar. The other family of ways to get standard errors, I think, are becoming more useful. They are computationally harder. There's more under the hood that has to be done, but I wanted you to know of them. And these techniques tend to use some kind of resampling by which when you take your data set and you sample from your data set, there's various kinds of this. You might take a sample from your data set of a certain smaller sample size and leave one out, or do it with replacement or without replacement. Some specific examples of those are given here. But the idea is that rather than trying to apply the logic of asymptotics, what would happen across repeated samples that you don't have, you just use resampling with your own data to try and come up with an empirically derived standard error instead. Um, Statistical analysis that is done via Bayesian estimation, a technique known as Markov chain Monte Carlo, is related to this approach. And if you're interested in finding out more about this, I would recommend Chapter 18 of the Mitchell book. Um, he talks about some of these methods. And also in PSQF 4143 with Dr. Brandon LeBeau, I believe he uses these sorts of empirical sampling errors to do in some of his demonstrations as well. Okay, so the big picture, what we talked about, trying to get ways of describing univariate statistics for one variable, central tendency and dispersion, and then talking about how to get standard errors for those statistics. That would then allow us to make extrapolations from our sample to the population. We focused on just central tendency for quantitative variables, and then what I just talked about for binary variables. I did want to just plant the seed that these general ideas of standard error show up for other statistics as well, such as for dispersion. So just a little bit of information about how one might come up with a standard error for a sample variance. So the fancy way of describing a sampling distribution for a statistic, such as the mean in this case, looks like this. So what I'm saying here is that the sample mean, y bar, for any sample S, this squiggle thing, this is a tilde, it refers to the type of distribution that variable is supposed to have, and the capital N here means normal. And I'm saying that the center of that distribution is the population mean mu, and the standard error, that what we know of as the standard error, is its standard deviation. And so it looks normal with larger sample sizes, but it's closer to t if you have smaller sample sizes. So this works out just fine for the sample mean of quantitative variables, but it doesn't work out as fine for other statistics like the sample variance. Well, the problem with that is that both the normal and t distributions are symmetric, they're continuous, and they can extend from negative to infinity to positive infinity. And that range of possible values doesn't readily map onto what the possible values of a variance are. So just as a question here, what do you think the smallest possible value for variance is? Well, 0. So if I had a variable that looked like this, if everybody got a score of 0, there would be no variance. This actually has a name. It's called a degenerate distribution. I would call it a constant. A variable that has no variance is a constant. Everybody got the same score. That's the lowest value for variance that you can have. Variances can't be negative. Therefore, sampling distributions to try and standardize a given variable sampling distributions using t or z isn't going to work because those include negative values. So what can work? Well, it turns out this other thing called chi-square can work. So we need to find a sampling distribution that takes into account that the smallest value of variance can be is 0. And the larger the variance is, the more it can potentially differ across samples. So if you have a variable that has very little variance to it, if you sample repeatedly from that variable, your samples are going to have variances that are more alike because they just don't have anywhere to move. They're going to be very close to 0. The more variance that there is, the further it can wiggle. And so what the behavior is for the sampling distribution of the variance depends on not only the number of subjects, but also the amount of variance. And again, people smarter than me figured this out, that you can use the chi-square distribution to help approximate the sampling distribution of a variance. And it looks like this, where we have a ratio of the sample variance to the population variance, weighted by the sample size minus 1. That's our friend denominator degrees of freedom. That ratio is distributed as this x-looking thing. That's chi. So we call this chi-square, where chi-square has degrees of freedom of n minus 1. And so here's a picture that shows what the chi-square distribution looks like under different degrees of freedom. And so if it's very small, like degrees of freedom 1, it takes this black line, the red line if it's 5, and it starts to look a little more normal as you get further out. So that means that the more people you have, the more symmetric the distribution would be for how the variance would differ across samples. But the smaller it is, the more it's going to be closer to this boundary. Now, I don't know about you, but thinking about an x-axis as a ratio makes my head hurt. And so in trying to figure out for myself how to explain this to you, I came across this person's YouTube video. I have no idea who this is, but it was an excellent tutorial, so I encourage you to check it out if you're curious. But the high points here is he discovers a way to try and figure out how to plot as the x-axis of these sampling distributions what the sample variance actually is. So these plots match the same ones that I was giving you with respect to the sample mean. So if we have a sample variance on the x-axis here, and what we're plotting are samples from a variable whose population variance is 1. And each of the samples that I take from this population variable are sample size of 5 each. The distribution for what the sample variance is looks like this. It's positively skewed because it can't go below 0. So this is kind of a classic chi-square looking shape. As you increase the sample size that you take from the population variable, if you grab repeated samples of 20, then you start to see that the sample variance looks a little more symmetric and normal distributed. So it starts to behave a little better in terms of looking like other sampling distributions for other statistics. But it's this situation down here where you would have a harder time describing confidence intervals or standard errors because this thing isn't symmetric, and any confidence interval that you would compute needs to take into account this type of asymmetry. So the chi-square distribution doesn't hold as closely for variances of variables that aren't normally distributed. And that's a whole nother story beyond what we have time for. But the standard error of the variance is not typically something that would be of concern. So it is technically possible to do hypothesis tests that would compare a standard deviation from a sample to a standard deviation of a population. I have never seen that in practice, and I would have to look it up to figure out how to do it. So the standard errors of variances or standard deviations tend not to be a thing as much as they are for means or what we're eventually going to have in modeling contexts of intercepts and slopes. So in practice, any parameter, any number you care about, let's go with that as a definition for now. The software will give you a standard error that goes along with it. That tends not to happen for variance-related terms, at least as long as you're working with closed form types of analyses where all of the answers could be calculated by hand if you wanted to. For more complex problems that have to be solved via iterative algorithms, the standard error will be provided because it pops out of that later process. And just as an aside, I'm sure there are rules and formulae that I've never heard of that would allow you to calculate standard errors for other sample statistics that we talked about, such as the median or the mode for measures of central tendency, and skewness and kurtosis for measures of asymmetry and flatness, respectively. But again, I've never once needed to do so. I think in most cases, the sampling distributions of these are not known, cannot be approximated via some sort of ready-made formula, and you would have to use resampling type approaches, so your bootstrapping, permutation test, jackknifing, resampling family of approaches to be able to do that. So if you're ever in a situation where you need to get a standard error for these things, I would encourage you to look into these alternative ways of doing so via empirical resampling of your data. So that's it. I will post this video and tell you all to have a good weekend. I'll catch you next week. And as the children say, like and subscribe and make sure you get the merch.